Good morning. Welcome to this session where we are doing the exercise, the lab exercise for the NTNU subject or course called TPG4242 Advanced Drilling Engineering 3 for master students. At NTNU, as said in the previous lectures, there's a room with computers where Landmark would be installed on each of the computers. You are going to find login credentials and so on with me if you are planning to run it there, or you can just watch this video and get an idea about how this works. Of course, much more potential learning in doing it a little bit yourself alongside this video. You will see later on a short video describing exactly how to go on step by step in order to make your way at the NTNU computers. For this video, we will just do more a generic setup, how things are done. For those of you who are not going to do the exercise at those specific computers, this video would be probably the most beneficial. All right, what we're looking at here in the background will be compass. You need to start compass. You need to have a filing structure where you can go down to a certain design in one well, and with that you need to specify your well path before you can do anything else in StressCheck. The well path needs to be installed, and you need to be able to pick it up from compass before you go ahead and start StressCheck. All right, so as you saw, I shut down StressCheck in the background now. Reason being just what I said. We're going to use this depth reference. We're going to say that it's an onshore well. That's what you're going to do. We're going to say that there's no change like this. For this exercise, it's better to use no depth references whatsoever. You can see in the bottom here double elevation, air gap, ground level, all of these things set to 0. It's a thing in itself to get this right, and this place, this whole site is set to a land-based development. So that's why we keep that. It's still trying to force some workaround. That's not the level we want to start with here. All right, double click on the design. We're going to get a well path, and with that I'm going to talk you through the file with all the different data inputs. The survey is here. What we're going to do, we're going to copy out measure depth, inclination and azimuth like this. And compass very much likes numbers that have a dot and not a comma as a decimal separator. And once you know that, you will see that the survey with a dot instead of a comma is here. I have already prepared it. Yeah, and then we will paste it in, making the first blank column, and then import as this icon. Since it's copied to the clipboard, this option is available like this. Open, and it's delimited. The numbers are delimited in the file. It's a tab. You see how nicely they separate now. And we know that it was measure depth, inclination, and azimuth in the different columns. So for us, it's just to finish. And here we go. Here is the survey. We save, and off we go over to StressCheck. Yeah, so while StressCheck is starting up in the background, we can just have a quick look at the well path. I like to use this 3D viewer. So we will have a quick look at the well path to see that it's correct in StressCheck too, but in StressCheck it's a 2D viewer, not a 3D one like this. Yeah, so here we have StressCheck now. Here it is. And we'll find the same filing structure here. Let me double click on the sign. It will tell you about the template. Just click normal and OK. This one is just to say which unit system do you have, which tabs do you want in the bottom, so on and so forth. So that's just a small specification. The unit systems they are quite important. Start with it at compass tools. Let me see. Units are on top. Yeah, it's locked. It's locked in this version. Yeah, you're not allowed to edit it, and there's a reason for it. You mess around with the units and you may have a lot of problems. And that's why I said that you need to make sure that the units are okay. Yeah, again, in this version, for every single application, the units are locked. And that's fine for now, but you will have to do something in the NTNU system or the system that you are working on to make sure that the unit system is unified all the way through your whole project. The project meaning your well, or even maybe the well site. The whole field development. All right, let's double click on the design to open it. It is open. You can see that since it's bold. So this is the one that we're going to have and to look at. All right. What I like to do now is to go to File, workspace apply, and then I would like to choose this one. This is a workspace that I've defined for myself. What it does, it tells us which tabs will be predefined. If you don't have a workspace defined, you will have 3 simple tabs there, and you need to add more in order to go directly to your desired view. Otherwise, you will have to, and then changing, you have to change for each single one of these ones, and that's more work intensive than just having them prepared here in the bottom. You'll see what point I'm trying to make better once you have worked on it. All right, we go first to the well path to see that it's correct. So that's the plan view, and we have the section view here. Yeah, you get an idea about the tab and why already, I guess. Now we are going to define the tubulars that are to be installed. I'm taking the cost because that's something predefined in landmark and not related to anything else, so to avoid confusion. We are going to upload the planned casing program, which is listed here with all the different details: hole size, size of the casing, type of the casing, 309 pound per foot X52, etc., and cement heights, liner placement, so on and so forth. Everything is here. Now this is a very special well construction. You see there's an 8.5 inch section going through the reservoir. There's a liner and the 14-inch casing that we are installing. As a matter of fact, as you see, if you place the production packer down here or if you place it here, regardless, it's going to be exposed to the annulus, meaning it's going to be a production casing. There's actually no intermediate casing in this well construction, and yes, it's a real well somewhere, and from my understanding, this has to be an exploration well, never meant to have a production packer. It is likely to be just plug backed, investigate the reservoir and then plug back, and then off we go, adding the different casings. 30-inch, it is called a conductor, that one, and it's a casing. The hole size is 36 inches. The hanger is at 0 meters, and we are going to say that goes down to 270 meters, and the top of cement is at the hanger 0. Next one is a 20-inch. That is the surface casing. It's also a casing. The hole size will be a 26-inch. Hanger is at 0, and the shoe depth was 1095. Top of cement all the way up. Now comes the one that we are going to have a look at, the 14-inch. And we have to call that a production casing. It's a casing. And the hole size was 17.5 inch. Yeah, and the hanger is at 0. We're going down to 22 10. Propose cement. Let me see. Propose cement at 1547 liters. Yeah, and the mud weight should be put into wait for the respective section. That's weird. This is a liner, all size being 12.25 inch, and the liner hanger is at 2109, and the shoe of this section is at 4155. Proposed cement 3655, and it's 1.75 baht. What we're going to do is put in a 7-inch reservoir. We can see in the casing program that there's no casing planned for the open hole, but we're just gonna throw in something. It doesn't matter for our analysis, basically because we're not going to analyze that section, but it's gonna not confuse StressCheck. Yeah. Papa? Yes. Papa? Proposed cement will be the same as the hanger. And the mud weight is 2.01. Like that. Finally, also not the part of the analysis, the tubing. Hanger is at 0, and we're going to stick it into the 7-inch liner. So the liner hanger we just had will be at 4055. Yeah. All right. So the active casing is a conductor, and we're going to say now okay, yeah, that's fine. Let me see if that's the correct one. No, that's not the correct grade. It's X52. All right. Yeah. That's okay. And now we need to switch to the 20-inch up here. It starts at 0. This option is allowing you to switch. If you have a 10 3/4 by 958, for example, you can make a split so that there's 10 3/4 here and then 958 down here. That's how we split between them. Let me see the weight for a 20-inch, 133, and the grade 310. Yeah, not available here in this version. Don't know why. 14-inch goes from 0. Let me see the pound per foot. That's correct. 125. That's correct. And then let's go to the 7-inch. Landmark doesn't like blanks, so we need to fill in for all the different sections. Then top of the liner being 4055, and we're gonna have such a heavy liner. Switch to the tubing, which goes from 0. That's kind of a heavy one too, 5.5 inch. Yeah, that's monster tubing as well. Yeah. All right, now we can save. This is the complete setup. But in the schematic here, everything is set up, a full complete well. All right, this tab called work is where we are adding all the different pipes. We can for our pipe, if we are selecting the 14-inch, you might notice that I deviated a little bit from the casing program. It says 978-inch here, and available to us in the version that I was running was 958. It doesn't matter as long as this section is okay for this purpose. That's the one that we're doing the exercise for. So yeah, this one doesn't really have let me see, connection tubulars. Special connections inventory. Let's see. Yeah, I think we just skip the connections altogether in this exercise, at least for now. What we do is go to the geothermal gradient. Let's have a quick look at the geothermal gradient. It's going to be a specific temperature at a specific spot. Let's say 148 at the well TD, and we can put in additionals here. Note that it's the vertical depth and temperature, so let's see if we can find the temperature. Here it is. Yeah, so I copy that to the clipboard. It has all the correct data already there, and with dots. Then we press apply. Here is our temperature. The thing is, in Norway offshore, we don't have 26 degrees on the surface many days. It's more likely that it's 10 degrees. And the 148 that I put in doesn't really look very nice on this plot. When you are doing these things, you would get all the data from the subsurface team, and it's very important that that this data gets correct. 150 degrees being the limit for StressCheck. StressCheck will give you a surface temperature identical to the reservoir temperature and not model any temperature gradient, a real temperature gradient. So it will give you a lot more stress in the pipes from temperature expansion than more advanced software. Typically for HPHD applications, you're using WellCat, both for casing design and for tubing design. You will use WellCat always. So basically we are on the limit, but for this application we should be okay. Meaning the exercise and demonstrating how StressCheck actually works. So that's the geothermal temperature. Now let's do the pore pressure and the fracture gradient. What you'll see is that there's a tiny little knob in the corner here. I will drag it here. And there's a tiny one on top here too. Now we have 4 beautiful windows. And here I would like to have wellbore pore pressure. Okay. And the pore pressure comes in the vertical depth, pressure in bar in this unit system, and the specific gravity. Okay, so let's see if I have extracted that from the Excel file. Yeah, it's here. Okay. So click in the first available column and paste it in. There we go. In this window, I think I want the fracture gradient, and it's the same here. Yeah, paste it in the right format. There we go. And remember to save. Yeah, so this is what it looks like. And let's go back to the work tab. Now we are going to start with what I call the final input step. I like to follow this workflow in StressCheck that is designed. I believe it's only in this StressCheck now. It used to be in all landmark applications where you can step wise go forward. So for general, here is not much to put in. Press OK, and then next arrow. Pore pressure we have put in, and we have seen the plot. It's good. Fracture gradient is good. Well path we have seen it's good. We have seen the tubulars. Here comes the production data. Let's see packer data. We will see that the packer depth is a little bit off. It's at the very end of the tubing, which is not likely. Let's have a 50-meter tailpipe. Packer fluid can be water, that's fine. formation type, seawater type. Perforation depth is the absolute deepest point. There will normally be a shoe track there. So let's say 4270. And the gas gravity, that's gas compared to air, and that's 0.7. Okay. Design parameters. These are important. These are the NTNU design parameters. I think I will go for one. Same for connections as for everything else. Yeah. Design parameters and analysis option. We're going for a single external pressure profile and limit to frac at shoe. That's what we have been talking about in the lectures. And the collapse strength model is API, which is the industry standard. Press OK for this. And now to the next step. Cementing. Cementing mixed water sounds a little bit light. I want to use 1.39, I think. A slurry of 1.8 SGs is good. Displacement fluid is the mud. Float collar depth, typically it would be higher up than the shoe. Yeah, I think this is the standard temperature. So we apply here and so on. Next step. Tool passage. We will not do anything there. And here, ladies and gentlemen, we arrive at what is the interesting part. Now we're going to set up the load cases. And for drilling loads, displacement to gas, we don't need the gas kick profile as we have the displacement to gas. Fracture shoe with gas gradient above, lost returns with water. That's typically what we can do offshore, or if you have a good supply of water available. It's a philosophy question. Surface protection, pressure test, green cement test pressure, drill ahead. Yeah, that's what we have for drilling loads. Production loads, tubing leak, simulation surface leak, injection down casing, that would be a cuttings reinjection, and we're not going to go for that. External profile, fluid gradients with pore pressure. Alright, these are all burst loads. Now we have to go through every one of them. Influx depth, that's fine. At the very bottom should be the worst case. I like to use gas gravity. Fracture margin of error, we can say that there is a certain insecurity in the fracture margin, 0.1 SGs. Mud gas interface all the way to the top mud weight is defined. Lost returns with water, fracture margin, the interface, mud weight. This is a collapse load then. Yeah. And then surface protection, gas gravity, fracture margin, pressure test. The pressure test would be a result of the displacement to gas, and that should be 600 bar, and it goes up to 635 as we discussed in class. Any casing less than 16 and something would have a 35 bar added kill margin for bullheading, according to the NTNU requirements governing documentation set for casing design. You'll find a lot of good stuff in the casing design regulations. How to set up the loads, the load cases that we are now going through would be defined specifically in the governing documentation, supporting you in your job. Yeah. So, but what I'm gonna do now, I'm gonna simulate the displacement to gas, and we're gonna add those 35 bars later on. So for now, no pressure test. Tubing leak, here everything is set up. StressCheck has everything that it needs. Injection pressure, again, that's a philosophy question. From the subsurface team, you need to know, should I fracture this well or not? Should I pump and inject like the permeability allows without fracturing? And these figures in pressures depends also what kind of fluid density that you're pumping. So for now, I think we leave this one. Yeah, less than water. Could be some base oil there. Yeah, fracturing gas gradient above. Nothing here to add either. Green cement test pressure is the same. You need to have the test pressure, which I think arrives at 635 bars. Drill ahead burst, hanger depth, top of cement, shoe depth, mud weight next section, and equivalent circulating density. All of this correctly put up for already in StressCheck. And we tick off a pore pressure in open hole. We press apply. There's no more. There are no more new things to add here. Collapse loads. So drill ahead was put in as the collapse load, of course. Full partial evacuation. That's not well. Let's leave it in there. Cementing. Full evacuation. That's not gonna happen. It's not a gas injection well. Bow blow packer. Fracture pore pressure, and these are our load cases now. Yeah, nothing to add here. Cementing. This is good. Safety factor analysis. Let's see what that does. Yeah, good. You always have pore pressure in collapse cases, reducing the mud weight. We have to use worst case scenario. Even if it seems extreme and unlikely, we always use that as a design philosophy, giving ourselves the margins that we need, like that. Axial loads, running in hole, let's say 5 meters per second, and overpull 150. Yeah. I'm gonna put in 635 here. Service loads, apply. I have to adjust that load later on if my recollection is wrong. Here we go. So the burst loads would amount to 700 bars, whereas the design rating is it's better than that. But what we need to know also would be the wear tolerance. Flaps design is quite good. Actual design, traction design, yeah, swing sections, connections. Yeah, again, so this is what Landmark gives you of default numbers. We are going to you see these connections. They are not at all industry standard. They probably were released sometime in the 70s, 80s, and you'll find those in very few cases in your professional career. Yeah. All right, so we are now going to do different analysis. Let me see. All right, so let's get to it. We need to go to the triaxial in order to get a quick look, and that's what basically we are using the triaxial plot for, to get a quick overview to see that our design is okay. Now remember, the couplings they are not inserted here because it's the old obsolete types. Would never be these types of threads in production casing. We can have a quick look at the numbers. We know and remember that the pressure test is not good still. Let's have a look at the burst loads. Burst load data. Where is the the burst load tab is not coming, so we'll just have to find it. Tabular results, burst loads. All right, here it is. Displacement to gas, yeah, almost 600 bars in our case, and that means 635 as a pressure test, or actually 630 more or less, but let's just use the number 635. We will then go to burst loads, and we will go to edit, pressure test, 635, apply, and we also need to the see, yeah, 635, yeah, this is updated already. All right, and now we have to go back to triaxial, and let's see what happened now. Now we have a nice pressure test is the most extreme, which is what you're looking for. Yeah, and what I would like to do now, I would like to add a tab, tools, tabs. Let me see if it's already there. Yeah, let's use this one. What we will call it, we call it burst. Okay, and view burst plots, load line. Yeah, that's where we are. Actual load line, design load line. There's quite a good margin actually. Yeah, we see the support, and something happens at the 1600 meters. We can have a quick look at that. That's typically what we do to check what is going on. And I presume it's cement, just shy of 1600 meters. Let's see. Casing scheme, 14-inch. Yeah, just shy of 1600 meters is the top of cement. That's where. So below this point, we have some support. That's why it changes dramatically there, but still a good overview. And now we would like to have a quick look at, let me see, where's my burst again? There we go. What I'd like to see is the pressure profiles. We'd like to see that the pressure test is the most extreme, covering the whole length. Yeah, and tubing leak, displacement to gas. Okay, maximum wear. I wonder if you could switch. So for burst, this is for collapse, and burst is the most demanding one. Approximately 7% wear at 1900 meters. That's the most critical one. Yeah. So that's what you need to keep an eye on when you do your casing wear simulations. If the work that you're going to do simulates higher wear in the area here for the 14-inch, you need to go to a different casing or redesign the plant well path to yield less stress. There are also other things you can do, less wear, sorry, and there are other things you can do to mitigate wear, but normally choosing a different casing would be your first option to look at. There's a number of other things we could discuss also. What I would like to add for you guys, the help in Landmark is quite excellent. It's something to something for you guys to consider. There are all sorts of topics covered here. A lot of references to papers, and these papers contain references again, so you'll get a good and quick overview of what is going on in and behind the industry software for well paths, for casing, tubing design, for drilling applications like torque and drag, everything, kick tolerance, absolutely all pertaining to well construction is covered here in some way or another. There could of course be more modern things, and there are here and there topics that could theoretically be better covered, and that's for you to look at and find out. Many students have found that the help itself is very good when you're working in Landmark, but also for other applications, references to look up to build your own knowledge and understanding. It's quite comprehensive as a support. Now, if you want to have the input file in Excel and do this do this exercise yourself and to look at the landmark and compare to the results shown in this little tutorial, then you just drop me an email and I will share the input file with you. All right, thanks. Hope it was meaningful and give you some support. Of course, we could dig a lot more into the details of support and so on, but I leave that for you guys to do. And here is also where the help function could support you well to see the details behind every load case, not much deeper than covered here. And basically what you'll find is that most of it is covered in the lectures so far. All right, thanks.